So we now target the part which brings out series, the higher order derivatives of functions. If the function f of x is equal to x to the power 7, then the first derivative is going to be 7x is going to be 7x to the power 6. Then the second derivative, you differentiate the first derivative. So it will be 7 multiplied by 6 x to the power 5. And then third derivative, you differentiate the second derivative. So it will be 6, 7, 6, 5, x4. And then the fourth derivative of x, it will be 7 plus 6 plus 5, 4, x3. So you have to understand that from the very function, as you differentiate, you will develop a certain pattern that you are able to follow to give a general statement about. So in this case, I'm able to see that this thing is somehow related to the factorials, depending on the position of depending on the end that I'm dealing with. So if we go to examples that are coming from the tutorial sheet now, example 1. Find the higher order derivatives. Take part A. We have y is equal to 3 minus 2x to the power 7. We say the first derivative, we use chain rule, where we have 7 and then 3 minus 2x. 7 minus 1, we get 6. And then differentiate the inside. The derivative of 3 is 0. And the derivative of negative 2x is negative 2. This is negative 14. 3 minus 2x to the power 6. Well, we also asked to find the second derivative. This will be negative 14 multiplied by 6. 3 minus 2x to the power 5. Multiplied by negative 2. So it now becomes positive 28 by 6. 3 minus 2x to the power 5. The third derivative, that is 26 in 28, 6, now 5. And then 3 minus 2x, 4 minus 2x. So this is 28, 6, negative 10, 3 minus 2x to the power 4.
Excuse me, sir.
Okay.
Is it supposed to be negative 2 or 2x?
Negative 2 just.
On the 2 just, yeah.
Yeah, it's supposed to be just -2.
Thank you.
Okay. And then when you multiply it, we have -10. So unless otherwise, my target normally is to try by all means to dodge the tutorial sheet. Since you are having the tutorials solved by the, including tutorials. So when I do that, then I prepare my short notes and presents my short notes. As I present my short notes, then I can pick 1 or 2 from the tutorial sheet, those that I suspect to be a bit tricky. And some easy ones to be used as examples, also together with some trick ones. I think it's a bit okay with me. I don't know if that will sit well with you.
Yes, sir.
Okay. So after presenting the tangents, then now we talked about a bit of some derivatives, but you realize that what you're doing here is you want to get to some pattern that you're able to understand. But before we can talk about those nice patterns, maybe we can also pick something from question 7 of our tutorial sheet 2 that is entirely based on our first session, which was on tangent, where we have to find the equation of the tangent to the given curve at the point. So let's pick the first case where we have x squared, and then we have y3, and then we have minus x3, then we have y2 is equal to 12 at a point -1, 2. Let's see what we get here. So we know that the target is to find the first derivative here. That is called the gradient of the equation. The gradient equation. So to differentiate, always when we are unable to solve for y, you differentiate using implicit differentiation. So in the case of x squared y3, this becomes a product. So we differentiate x squared, it will give us 2x, and then multiplied by y to the power 3, and then plus, we now differentiate y3, we get 3y squared multiplied by x squared. But because we are now differentiating y, we attach a dy and dx minus, we differentiate x3, I will have 3x squared multiplied by y squared, and then minus still so
Excuse me, sir.
hello.
On the middle x, does it change or it still remains the x cubed?
The middle x, when we
Before dy
differentiate,
dx, is it not still x cubed?
and now for the mid one, this one, it was x
Yes, that one.
squared here, so it remains x squared.
How about there on top?
Then this one now, the x cube,
That one. Yes,
is
that
one
is
now
the one I was.
we're differentiating here first.
Oh, okay. The whole of this part up to dy dx is the first one, x squared y cubed. Okay.
Yes. So now I got the next one. So we'll differentiate y and keep the x cubed and then multiply by dy dx and differentiate 12, which will give us 0. For easy simplification here, our target is to find dy dx. So wherever there is x, we'll take -1. Where there is y, we'll take 2. So what we have now is 2 multiplied by -1 by 2 to the power 3 plus 3 multiplied by 2 to the power 2 -1 squared dy dx, and then minus 3 -1 squared 2 squared minus 2 -1 2 to the power 3 dy dx is equal to 0. So that we get -2 by 8. This will be -16. And then that is 1, 4 by 3. We get 12 dy dx. And then minus 3 by 4. We get 12. And then plus, we get 16 dy dx is equal to 0. So that 12 plus 16, we get 28 dy dx, which is equal to -16 minus 12, that is -28, which becomes +28 when taken the other side. Then divide by 28, divide by 28. This will simply mean that dy dx is equal to +1. So this is the case, and we are calling this our m, the gradient. If this is our m, then we can find the tangent line. So say the tangent line is then the line y minus 2 is equal to 1, x minus -1. This implies that y minus 2 is equal to x plus 1. So that y is equal to x plus 3 is the tangent line. Should you be asked to find the normal line, then you know that your gradient here will be -1, and then you are able to find the normal line. So if you look at your questions there, you understand that everything here is just about everything here is just about really how we are good at differentiating any type of functions.
Differentiate, sir.
Hello.
Hello, sir.
Hello.
Yes, differentiating actually these figures without fractions is not a very big deal. But when they are surds, that's where, for me, I get confused.
Okay.
As well as the sines and the cosines and the cosine what's and can't. Those are the ones that confuse. Yeah. Tricky. Okay. This is good.
So let's look at question 6. It is saying find dy dx in terms of x and y, and then we'll pick c, which is x, and then the square root of x plus y is equal to 8 minus xy. So this is a bit of some product here. So we're dealing with x plus y to the power half is equal to 8 minus xy. Then now we start differentiating here. So here we use a product rule. So we're saying this is like our u, and this is like our v. This is like our u, and this is like our v. So now I'll say we differentiate first x to give us 1, and then multiply it by x plus y to the power half, plus you now fix x and then differentiate by dropping half. Then you get x plus y. You subtract 1 from half, it becomes negative half, and then multiply by the derivative of x. That is going to be 1 plus the derivative of y. That's going to be 1 multiplied by dy and dx is equal to, so you have to be careful where you put the dy dx there, is equal to, the derivative of 8 is 0, and then of negative x, we get negative 1 multiplied by y, and then you keep the x, then differentiate y, you get 1, and then dy and dx, like that. Then now, you put the dy's, our target is to put dy dx together. So we have, we can expand the left, so we get x.
Sorry.
Okay.
I'm lost on second pointing.
The second point where we had to change the root to half.
Yes, sir.
So there, we're just trying to understand that what is actually called the root is just the power half. So you can as well write, when I see a square root, I can work with the positive 1/2 instead of the root, especially where differentiation is concerned, because
No, sorry, sir.
Okay.
Not where after those in lead markers, how we're differentiating everything down there.
Okay. The actual differentiation now.
Yes, sir.
Okay, so the first one we said, this is u. Since we have a product here and we cannot expand, so we differentiate x, we'll get 1. And then multiply it by the whole thing, x plus y to the power half. That's why you're seeing x plus y to the power half here. Two, you differentiate, you now fix x. So x is fixed. Then you differentiate x plus y to the power half. By dropping half, keep everything as it is, x plus y. To the power, you subtract a 1. It now becomes negative half. This multiplied by the derivative of the inside. So we're now differentiating the inside. Derivative of x is 1. Derivative of y is 1. But because it's y, we write dy dx is equal to the derivative of 8 is 0. Negative xy, you differentiate with respect to x, you get negative y. With respect to y, you get negative x. But whenever you do with respect to y, you also write dy and dx to explain that it was with respect to y here.
All right, I get the point now.
Okay. So now we want to put the dy's together. So I'll write the x plus y to the power half as just that root plus x over 2 root x plus y. Now, because half has become negative half, I can push it in the denominator as a positive half, so it becomes a root multiplied by 1. So I just have this thing, and then plus the very thing over 2 the root of x plus y. And now I'm multiplying with dy dx, so I'll have a dy dx here is equal to this, so that I can now put the dy dx's together. So dy dx is equal to, so if I push the one on the right, I push it to the left, then I'm going to have x over 2 the root of x plus y plus x is equal to minus y minus the root of x plus y minus x over 2 the root of x plus y. So that now what we'll say is dy dx is actually negative y minus the root of x plus y minus x over 2 the root of x plus y. This whole thing to be divided by x over 2 the root of x plus y plus x by this whole thing. So one may attempt to simplify, but nothing much will change there. The question that I'm very much interested in is question 8, part 1. What we have is xy is equal to x plus y. The question is asking for y prime prime in terms of x and y. So how do you connect from the first derivative to the second derivative when you are actually using implicit? So suppose we use, because I know here you're able to solve for y and then have an easy differentiation. Now, we want to assume that we're not able to solve for y and we have to do implicit to get y. Then how do we get the second derivative then? So it will be the first one. You differentiate xy with respect to x, we get y, plus we differentiate x with respect to y, and we get x, so dy dx is equal to 1 plus dy dx, like this. Then this one here will now say we can solve for dy dx, so that we have dy dx is equal to 1 minus y over x minus 1. Then to get the second derivative now, you differentiate this one. It becomes d2y dx squared. When you differentiate 1, that is 0. So here now I'm using quotient rule. So where the numerator is u is 1 minus y, then its c prime is going to be negative dy dx. So before you rush to substitute, look, this dy dx is the one that we have found as the equation. So this is negative 1 minus y over x minus 1. So that we get y minus 1 over x minus 1. Like this. Then you get y prime, we get v to be x minus 1, and then v prime will just be 1. So remember, this one, we're using it to find the u prime, because we understand that this should be v prime v minus v prime u over v squared. So that means that d2y over the x squared is equal to u prime, is what we have put in here as y minus 1 over x minus 1 multiplied by v. V is just x minus 1. And then minus v prime is just 1 multiplied by u, and the u is 1 minus 1 over v squared, and that is x minus 1 squared. Like enough, this and this can cancel. So get 1 minus 1 minus 1 plus y. Then expand over x minus 1 squared. This is giving us 2y minus 2 over x minus 1 squared. So this is how we plug out the second derivative. So I just wanted to mention that when you're heading to the second derivative via first principle, it's important to note that once I have the separation, where I'll get dy dx, I must be quick to substitute it with the actual dy dx in terms of the variables, so that it becomes easy for substitution. Because if we maintain the negative dy dx, then we'll be confused in the substitution. We end up not knowing which one to touch. I hope we don't have questions. So stick to the clock now. So next, my first year will have tests this weekend. So I'm sure then they will be off learning. They can just learn once in a while. Because they are going for a recession there. Then we can capitalize now that time preparing for the tests as well as need be. You can always adjust. So that we end here for the night.